is now at KIPP and before at Stanford, and he's going to tell us some new ideas of black hole entropy in 2+1 dimensions.
That's right. Thank you for the invitation. Thanks for having me here. So I'm going to talk, as Nemanja said, about a certain class of black holes, but let me try to kind of contextualize and set the stage a little bit about why at least I care about these sort of space-times, because there are a lot of different kind of, maybe orthogonal things at play. Maybe write a little bit bigger. Okay, so here are the space-times that I'm going to be interested in. So if you just look at this piece here, this should hopefully look familiar. This is just anti-de Sitter space-time, and people are obsessed with this for all sorts of reasons. Well, I guess maybe one reason, ADS-CFT. There are all sorts of sub-reasons within that. What I've written here, there's this sort of conformal prefactor. So I'll explain where this kind of R to the 2 theta pops up. So ADS-CFT, as probably a lot of you know, was originally discovered by considering certain solutions in string theory. So if you consider a stack of D3 branes, this is the gravity background sourced by those D3 branes in a certain limit. Once I put in this factor, this is closely related to the same type of situation, except now you have a stack of D branes for P not equal to 3. So you generally have DP branes in string theory. When P equals 3, the background is ADS. When P is not equal to 3, the background looks more like this. There are sort of compact spheres that come along for the ride, and I've sort of dimensionally reduced the formula. But the point is, in string theory, for certain values of this parameter theta that I have here, these are backgrounds for stacks of branes. So that's one reason to kind of care about it, because people tend to focus on ADS in the context of holography, but these backgrounds are also interesting. There's, in the past few years, it's sort of come up, and actually this notation theta refers to the notation in the past few years when people have been doing kind of applications of holography to condensed matter physics. So these spacetimes people call hyperscaling violating spacetimes. Hyperscaling violation is just some effect familiar in condensed matter systems. The theory is basically scale invariant, except it has an anomalous dimension for the stress energy tensor. So people use this to model, they use it to try and model non-Fermi liquids and things like that. I'm not really going to care about any of those applications. I'm just going to care more generally about the holographic interpretation of these spacetimes. Two more reasons, kind of personal to me about caring about these, is if you look at this, if you kind of do a double Wick rotation to the spacetime instead of a radial coordinate r, consider a time coordinate t, then this spacetime is just flat FRW cosmology. Okay? And for certain reasons, I care about flat FRW cosmology, so one might hope that by understanding these spacetimes a little bit better, you can maybe understand the holographic interpretation, if any, of flat FRW cosmologies. Okay, I'll give one final, yes.
So this is maybe a trivial question, but suppose you just do a coordinate transformation, r to the 1 minus theta equals rho, then that's going to be just ADS, but with a 1 minus theta squared in front of the d rho squared. You can stick a 1 minus theta squared in front of the dt squared and the dxi squared, just constantly rescale those coordinates, and it looks just like ADS.
Sorry, no, if you do the coordinate transformation, you'll get, if you try and get rid of this factor out front, then the dr squared piece will not be 1 over r squared.
Ah.
So.
Okay, right.
Yeah.
Yeah, okay.
Yeah. Good.
Okay.
Yeah, so this is, if you write down the curvature scales and things, this is a different beast.
Yeah.
Sure. Okay, the final reason I care, this is the thing that kind of motivated the stuff I'm going to talk about, is if you just notice that if you set theta is equal to 1 in this geometry, then this is just flat space. Okay? So I was curious about whether one can get intuition about the kind of flat space limit by taking a theta goes to 1 limit. So the more kind of maybe natural way people often think about flat space limits in holography is you start with ADS, and then you take the curvature scale large, and you take some sort of flat space limit like that. But this is a sort of weirder kind of limit where you take a limit through kind of different, qualitatively different spacetimes. But I'll get to that towards the end. Okay, so that sort of explains these spacetimes. I put a dxi here, but I'm going to restrict to 3 dimensions now. That's the case I'm going to care about. So in 3 dimensions, and I'll write the sort of black hole solution to this spacetime. Let's do it like this. T squared plus inverse r squared plus, let's call it 5. So I'm restricting to 3 dimensions now, and I'm compactifying the spatial coordinate into an angular coordinate, periodicity 2 pi, and then blackening factor looks like this. RH is the location of the horizon. There's some theta-dependent power here. And I haven't told you yet what theory this background is a solution to, so let me do that now. It's basically Einstein gravity coupled to it's Einstein gravity coupled to a scalar. So all these numbers are not important. I'm just trying to show that the that it's a sort of theta-dependent action. So let me finish writing this. Okay, so here's the action. I'm going to put two more pieces that are going to become important as we go along. So here's Einstein gravity, here's the scalar's kinetic term, and the potential, some exponential potential for the scalar. Yes?
Could you break the piece of chalk in half so it's not speaking?
Is that how you solve that problem?
Yes, it's a vibrational mode that its frequency is now beyond what we can do.
Fantastic. Okay, thank you. Beautiful. That feels a lot better. Okay, so I'm going to put in the kind of boundary term, which we'll get to later. So here's the action. This is the Gibbons-Hawking boundary term that again we'll come to later, and this guy is a counter term, which we'll also come to later in this part of the talk. I'll try and kind of refer back to which part we're on as we go along. Okay, so there's the action, and since there's a scalar field phi, I should tell you what its solution on shell is. It is that. That's the solution of phi on shell. Okay, so I have a bunch of formulas on the board. That's great. Let me now talk again about sort of this space-time here. I'm going to highlight the one thing that's going to be crucial throughout this talk. It's just going to be effectively the one fact I use to get the result that I want. And and the point is that this background has some number of symmetries. So it has rotations, or I guess we're in symmetry. There are boosts in the tx directions. That's a symmetry. So boosts and translations in txi. So if you leave out the radial coordinate. And it has a kind of funny thing, which allow me to call it a scaling symmetry for now, which is you scale the coordinates in this way. So if we ignore this factor here, this is just a scaling symmetry of anti-de Sitter spacetime. Okay, you scale these, the metric is invariant. It's a real isometry of the spacetime. Here, this r to the 2 theta kind of mucks that up. So I'm going to do something a little bit weird. I'm going to rescale the curvature scale. Okay. So this is not really an honest isometry. Doing this is really sort of changing your theory, but we'll see how it's useful nevertheless to kind of control what's going on. And the point in writing down these symmetries is, I said that this is going to be kind of a holographic talk. I'm going to assume that whatever field theory is dual to this background inherits these symmetries. And I'll say precisely, well, semi-precisely what I mean by inheriting this symmetry. Okay, I think that's everything I want to talk about in the introduction. Any questions about this space-time or this setup? So the idea, I guess I haven't even said what I want to calculate. The idea is that this black hole has some, Bekenstein-Hawking entropy associated to it, and the idea is to try and give a microstate interpretation to that entropy. So this is something people were kind of obsessed about in the 90s. Some people are still obsessed about it today. But the idea is this black hole has an entropy A over 4G. Okay, if you just look at the metric, it's pretty easy to write that down. It looks like this. And if I write it in terms of the temperature, it looks like so here's the entropy of the black hole. And the idea is to try to reproduce this microscopically. Let me just make sure I've written that down correctly. Good.
May I ask, when you consider the solution, do you first write down the solution and find the action, or you write down the action and find this is the solution?
You can do it either way. I'm not sure what you mean by the question.
From your point of view, which is more natural? Which one do you come up first and then try to find out?
So, I mean, this action is sort of natural from the point of view of, I guess, truncations of string theory. So one of the original ways that people wrote down these spacetimes is by considering this kind of truncated action and writing this down as a solution. It's not really going to be important to my talk, which way I go. I'm also going to claim it's not so important what the matter part of the action is for the things I'm going to say. I picked this one because to me it's the simplest one that gives this background. But it's not so important for the purposes of this talk.
Right. So along those lines, actually, the theta, I'm just trying to check, the theta equals 1 case.
Yeah.
There's a special limit of those so-called black strings that Gary Horowitz and collaborators studied in the early 90s, I believe.
I talked about the theta equals 1 case. So everything, all the steps I do in this derivation are kind of going to break down if you set theta equals 1 from the get-go. So instead, I'm kind of going to do it generally for theta less than 1 and then just take a limit.
Okay.
It's going to be kind of weird, but that's not the main thrust of this talk. That was just what motivated me to look at these things. And in fact, this black hole spacetime for theta equals 1 is not really even a black hole. It's just Rindler written in funny coordinates. So you can kind of rescale R and you'll see that it's just Rindler spacetime.
Okay. Mm-hmm.
Yeah. So, okay, that's the question. We want to reproduce this formula from a field theory calculation. Yes?
So this scaling symmetry, is that a symmetry of the action?
Yeah, so it's good. So I said that it's a symmetry of this background, but the more important thing is that it is a symmetry of the on-shell action.
Okay, so for your scalar field, that's a shift symmetry, right?
The scalar field by itself, the on-shell scalar field breaks the symmetry. Yeah, but if you evaluate the action on shell, the symmetry is preserved, even up to the boundary and counter terms.
Okay.
Basically, this is where phi appears, there's other stuff
But
going on.
L is in there, so it's
It's
like a
supersymmetry.
Theorem.
Yeah,
Right.
Uh-huh.
yeah, okay.
That's right. Okay, so I was hoping to keep these up, but I don't think I have enough board space. I may have to come back and erase this stuff. So the idea is to reproduce this. Good. So the one situation which I'm basically going to effectively completely copy is the case in ADS3. Okay, if I set theta equals 0, by the way, like I said, this is ADS3, and this black hole geometry is just a BTZ black hole. And here we do have a field theory sort of understanding of the entropy of the black hole, and that's just provided by the Cardy formula. Okay, so let me, doing too much boxes. Let me just, let's revisit the theta equals 0 derivation. So the idea is that you start with 2D CFT, okay, and you place it on a torus. So the torus, for our purposes, is just going to be understood as an identification of the plane. So you start off, let's say, 0. Okay, so let's say this is just a complex plane, and you have two cycles. One of them has period beta, that's the inverse temperature. And the other cycle, by scaling, you can sort of set to 2 pi. And really, you should, again, imagine that these are identifications that, produce a torus in this way. So the kind of simple argument for the Cardy formula of 2D CFTs, or one way to state it, is that you can do a rotation. Sorry. So you can rotate this 90 degrees to exchange the cycles. And then you can do a scale transformation, so the torus was originally here, and then it got moved down here. You can do a scale transformation to reset the size of this cycle to 2 pi. And then you can translate upward just so your torus kind of ends up back where you started. And the point is, these transformations are symmetries of a 2D CFT. All it is a rotation, a scale transformation, and a translation. So the theory should be invariant under this. What's the content of that statement? The content of that statement is that the partition function, as a function of beta, okay, is equal to the partition function at 4 pi squared over beta, because the only difference between this and this is the temperature. In one case, the inverse temperature is beta. The other case, the inverse temperature is 4 pi squared over beta. Okay? And then how does the Cardy formula proceed? Well, you can write the partition function. This is sort of the usual thing. In this way, this is a degeneracy at energy E. And now I can swap beta for 4 pi squared over beta. E to the minus 4 pi squared over beta times E times G of E. Okay? Why is this useful? Well, it's useful because if I take beta small, then you can see that there's a relation that relates the theory at high temperature to the theory at low temperature. Okay? Specifically, if I take beta small, in this form of the expression, you see that these exponential suppressions become huge. Okay? They become huge, and they basically project this theory to the ground state. So if I take beta to 0, then I get that z of beta is approximately e to the minus 4 pi squared over beta times e vac. And I assume that the degeneracy of the ground state is vanishing. There's a unique ground state. Of course, this is originally this is a CFT with no scale, but on a torus there are two-dimensional things. This length, which I've set to 2 pi, and the inverse temperature beta, and it's really the ratio of these two that's the important dimensionless number. And when that number gets small, the partition function projects to the ground state. All right. So once I have this, I'm effectively done. I can extract the degeneracy by doing this kind of integral over the complex beta plane, and this gives me the answer. I won't proceed with that because I want to generalize to theta not equal to 0 and do it in that case. Okay. Any questions about this derivation in 2D CFTs? All right. So the one thing which I should emphasize, and Actually, Cardy's visiting Santa Barbara right now, and actually I apologize to him for attaching his name to something that's not as powerful as what he wrote down. The nice thing in 2D CFTs is that you know what the ground state energy is. Okay? If you just conformally map the plane to the cylinder, then you could track the transformation of the stress energy tensor, and you could find that the energy on the cylinder is minus C over 12 or something like that. So you have a universal characterization of the ground state energy on the cylinder. And here, we're on the cylinder at finite temperature. In my case, I'm not going to have an argument like that for the ground state energy. Okay, I'm going to have to cheat a little bit, but there's going to be an assumption of some kind of bulk geometry that's smooth and regular and everything like that that serves as the ground state geometry. Okay, so that's a key way in which this formula is going to be weaker. All right, so now let's consider theta not equal to 0. So I said that boosts and translations are symmetries of this background, and boosts in Euclidean signature, because this is a Euclidean CFT argument, are just rotations, right? So this step where I do a rotation, and this step where I do a translation, I mean this one's not so important, are still symmetries of the theory, so I can still do that. This step here, the scale transformation, is not a symmetry of my theory, but I have this other weird thing. Right? It's a scale transformation where I also rescale the curvature scale. Right? In the field theory, this is kind of weird. This is like changing the theory. So whereas in a CFT where you relate the theory at high temperature to the same theory at low temperature, the way to think about this is that you're relating the theory at high temperature to a different theory at low temperature. But you know exactly how it's different because of this scaling. All right, so here, you just put in what the steps were. This is a rotation. There's a translation. Here, I'm going to do a generalized scale transformation. Okay? Then you should also ask this L. This is a parameter in the bulk theory. This is the curvature scale. Okay, so there's a question of what is L in the dual field theory. Okay, I mean the way to state it precisely, if you're in ADS CFT, for example, then L combines, L is L ADS, and it combines with L Planck to give you the central charge of the field theory. So this is kind of like rescaling the central charge or rescaling the N of the theory. The point is that the energies that I have are going to scale with some power of the curvature scale. Okay, without a microscopic theory, I don't know exactly how that's going to be, but these E's are functions of L, and the rescaling is also going to rescale these E's. Okay? So, we want to proceed with that. So in this generalized scaling, I'm going to want to take L to, so the scaling was by 2 pi over beta, right? That's what rescaled this to 2 pi, and this to 4 pi squared over beta. So L is going to go to 2 pi over beta to the minus theta times L. And again, let's talk about holography for a second. These energies can depend on L in various ways. So, in an ADS CFT type of example, you can have gravitational states in the bulk. These energies scale sort of linearly in L. You can have kind of heavy string states. These states scale as like the square root of L. You can have just perturbative fields, which don't even scale with a single power of L. They're just some function of L. But the argument is going to be that for this derivation, I only care about the gravitational states in the bulk, things like black holes or the ground state geometry. And for those guys, the energy is going to scale linearly with L. Okay, this is just a bit of a cheat for the purposes of this talk. You can do better.
So you're thinking those will dominate? Is that?
Yeah, exactly. So right. The thing I project to, this kind of vacuum state energy, I'll sort of show later, we'll see when we construct it, that this thing does really scale linearly with L. And we know that the black hole states scale linearly with L because you can just compute their energies. So we'll see all that in due time. But that's the assumption. For simplicity, I'm going to assume all the states, just so I can do this derivation cleanly, assume all states scale linearly in L. Okay? And like I said, you can be more careful about this assumption and do better, but I won't do that today. All right. So let's just retrack our derivation now. This isn't really the symmetry anymore, because we also have to do this other transformation. So let's get rid of that. This is the partition function. And we take the temperature still to 4 pi squared over beta. But then we need to rescale the energies. All right? So I'm going to drop these G of E's as well. That means that I need to put this factor here. 2 pi over beta to the minus theta times E. So this is a rescaling of the energies as well, because they're linear in the curvature scale. Good. But now we see that as long as theta is less than 1, which is the case I'm going to focus on in this talk, then this overall is an inverse power of beta. So when you take beta small, this still does the projection in the same way, as long as theta is less than 1. And this is also why I said if you set theta equals 1 from the start, everything kind of breaks down. Because if I set theta equals 1, then the betas cancel, and there's no sort of projection happening at small beta. I mean, none of this makes sense at theta equals 1. So, okay, let's take beta goes to 0 then, assuming theta is less than 1. Then we have a different projection. Then we have that z of beta is approximately e to the minus 4 pi squared over beta times 2 pi over beta to the minus theta times E vac, where again I assume the vacuum is non-degenerate. Good, but again now with the partition function I'm effectively done. I can calculate the entropy, the thermal entropy either directly by doing beta m plus log z, or I can do the what I've written before, which is just this kind of integral over the temperature and evaluate this in the saddle point approximation, but I get an entropy out by doing this. So let me...
Sorry, can I just...
Yeah.
Sorry, I probably should have asked before, but why, I'm not understanding why I should expect the energy to be order L. Why order L? Because if I look at, for example, if I look at your scaling, right?
Yeah.
Under lambda, right, when length rescale, L doesn't rescale like a length, it rescales as some funny power.
Right.
So why is it that...
Well, it's basically because the gravitational states are parameterized such that they have an L squared out front. So if I compute, which I will in a second with something like the Brown-York stress energy tensor in the bulk, or something that calculates the energy of these gravitational configurations, then they're just going to scale linearly with L because there's this L squared out here.
I guess that's something I should know, but I don't, I guess. That's the metric. If the metric scales with L, then...
Yeah, so yeah, I'll calculate that in a second. We'll see that it just scales linearly now. But it is true, in the actual full theory, there are going to be all sorts of states that scale with different powers of L. Don't even scale with a given power of L, they're just some function of L. But the point is going to be that the only ones I care about in this argument are the ones that scale linearly with L.
Another question.
Yeah.
So in this pseudo-modular transformation you're doing here, as you said, you're relating partition function of one theory to a partition function of a different theory with a different L.
Yeah.
Why should the central charge of those two theories, for instance, be independent of L?
Why should it be?
Or why should the temperature, for that matter, be independent of L? Why is this giving you theories with the same temperature, you think?
So, I mean, I'm not sure I understood the question. The argument was just that the theory is invariant under these transformations, right, and then I could just perform those transformations on the partition function.
Yes, and so that's going to relate the partition function of the theory that you're interested in to a partition function of a different theory. So your E vac there is the vacuum energy of a different theory, with a rescaled L. Right?
Yeah, so let me just, I mean, it is a different theory, but I can sort of, the point is that I've parameterized the different theory in terms of the original theory. Because the different theory is only different in this way. So once I kind of pull this out, then I can understand the different theory. This evac, you can really think about as in the original theory. Because this is the only difference between the two theories.
Right.
And so once I pull it out, then I parameterize that entire difference. So I know exactly how it's different, meaning I know exactly how to write the new theory in terms of the old theory. In a
Okay,
sense.
so in particular, you're assuming that the vacuum state scales, that the vacuum energy scales is L and F, and you're assuming that the vacuum degeneracy does not change in this scale.
Yeah, exactly. Right. Good. That's a good point. So I could have. Good. So I did a bit of a cheat for simplicity. There were these G of E's, and really, when I do the transformation, I should really be rescaling the E in here as well.
Right.
But the point is that once you're in the vacuum, since you're going to project to the vacuum state, if there's no degeneracy, then that rescaling is irrelevant. It'll change all the degeneracies of the, let's say, high-lying states, but it's not going to change anything about the ground state because it's not even a function of L, because it's just 1. Right? The degeneracy is just 1 if I assume that. Okay. So if I do the rescaling, nothing changes. But that's an important point, because in other examples that I won't get through, it's important to keep this factor in. Thank you for that. Okay, so unfortunately I'm going to have to, well, maybe I'll try and stick here as much as I can. So, okay, I said that I have this argument for the partition function. So what happens when I try and compute this? So, the entropy S is going to be, log of the degeneracy. And in this way of doing it, you're really doing it at high energies or high temperatures. That's the kind of Cardy regime. So this is going to be something that looks, well, it's a bit messier than the usual Cardy formula. Minus E back, 1 over. Okay. That is the claimed formula for the entropy. And again, I emphasize this is supposed to be sort of a microscopic understanding. This is counting the logarithm of the degeneracy at energy E in some purported field theory. Okay? And if I write it in terms of the temperature, because this form is not so illuminating, it looks like this. So that's, a bit promising. Maybe you could have seen it in the derivation, but at least you see that the scaling with temperature is coming out correctly. And that sort of follows immediately by this factor of beta to the theta that I had in front of energies E. That supplanted this T to the minus theta here, which matched the bulk Bekenstein-Hawking entropy. So now the question is up to the coefficient, right? So like I said, the vacuum energy in these theories is not universally determined. So one thing to emphasize is this kind of derivation I did with the rotation, scale transformation, translation. This is going to be true for any theory with a scaling symmetry. You don't really need the kind of local infinite dimensional symmetry of 2D CFTs to make that argument. The place where that's useful, however, is to come up with a formula for the vacuum energy, this minus C over 12, which is the Casimir energy on the cylinder. That's really the only step in the derivation of the Cardy formula, that and relating states on the cylinder to local operators on the plane, where the power of 2D CFTs is crucial. But where we don't have that, we can go sort of this far. So now I sort of need to make an assumption about evac. I need to make an assumption about what the ground state is. But to implement, let's say, this form of the formula, I need to do two things. So okay, let me go back here. So that's the formula. That's a generalized Cardy formula. Now to implement this formula, I need to figure out what E and evac are. So I have, E is supposed to be the energy of the black hole configuration, but I need a way of calculating that. Okay. So that's where the holographic renormalization stuff is going to happen. And I also need a proposal for what the vacuum configuration is and a way to calculate its energy. Once I have those, I can plug into here and see if I get this answer. All right. So that's going to be this part of the talk. So any questions before we move on to that? All right. So let's go ahead and do that. Okay, so how do we, in ADS-CFT and in more general applications of holography, the way people calculate the energy of, say, the dual field theory, and which seems to be robust and work in a lot of the cases where we can actually check things, is by calculating the Brown-York stress-energy tensor. So the Brown-York stress-energy tensor is given by this sort of functional derivative. And in this form of the action, it's sort of just picking up this piece. So this is the piece we're going to derive in a second. So you can ignore this. We're just going to differentiate, that k effectively, and this is what it's going to become. I'm going to erase all this now. All right, and I want to evaluate this, say, on the kind of empty background, where set these f of r's to 1. Let's not do the black hole, just do the empty background, and see what the Brown-York stress-energy tensor gives you. And it gives you a divergence. So if I evaluate at some small critical r, okay, the sort of boundary, the conformal boundary of this space-time is at small r. That's where we expect, the dual field theory to live. There's some divergence. So the formula looks something like this. So as I take RC small, remember theta is less than 1, this thing just blows up. It gives me nonsense. All right, so the method that was devised by Bala-Subramanian and Krauss is to renormalize this by adding local counterterms. Okay? There are different ways you can try to renormalize this. A thing that people did for a long time is background subtraction. You pick some reference space-time and subtract off its divergence from whatever space-time you're interested in. But the more kind of holographic version, I think, is to add a counterterm to your bulk action, which can be interpreted as a purely local counterterm in the dual field theory. And that's what this is going to be. So I claim, and because it's not illuminating to actually go through it, I'll just write it. If you add this counterterm to your space-time, if you add this counterterm, this is just supposed to be this, where I've put in with the beta and alpha r now. If you add this and then do the Brown-York stress-energy tensor, you'll get manifestly finite answers. So for example, now if I try and go and calculate this for this space-time, I'll find that the divergence, this gives a divergent thing that exactly cancels this. So the stress-energy tensor for this kind of empty background with no black hole is exactly 0. This is the same thing you would get in the sort of Poincare patch of ADS. Okay, so that's the counterterm, and now we can use this. We can go and compute, for example, the mass of the black hole geometry, where we have the f of r's in there. So the mass of the black hole, it's supposed to be, the stress-energy tensor is the energy density, so I want to integrate it over the circle to get the total energy. This thing is going to be right? Yes.
So sorry, just to make sure I'm following. So then,
Yes.
So the black hole thing is not a solution to this action then?
Sorry, it is. It's a solution to this action. Yeah. Yeah.
Okay, sorry. So
Yeah. Yeah. The empty background and the black hole background are solutions, but the same. Right.
okay, no, never mind. I got it. Okay, yes.
Okay, so this is what comes out, and again, without this counter term, I calculated this TT by doing this business over here, and I'm differentiating this part of the action. Okay, and without this counter term, I would have just gotten infinities. I would have gotten infinities like this one over here. And this is exactly the same thing that happens in ADS3. There, you sort of have a counter term that's just the induced metric. I mean, you don't have a scalar field in the problem, and you can see if I set theta to 0, this vanishes, and I just get square root of the induced metric. So that's the mass of the black hole. And this is going to be the thing that we plug into here, into this energy. All right, so we have one step left. To check the formula, we need evac. All right, So, like I said, I need to propose to you what the vacuum configuration is, and in addition, I need to calculate its energy. As we saw, calculating its energy just is this. So for the proposal for evac, let me write down the geometry, and then I'll talk about why that might be a reasonable thing. So ds squared of the vacuum is going to be L squared r to the 2 theta minus dt squared over r squared plus f of r inverse dr squared over r squared plus d phi squared over f of r squared. Okay, so what I've effectively done is I've, this thing is a solution to the same action. You can sort of see that by seeing it's just a kind of double Wick rotation of this black hole solution. And this is similar to what Horowitz and Myers did for higher dimensional ADSs. The thing that they call the ADS soliton is just this kind of double Wick rotation. And it has a bunch of nice properties. It is, it's regular, it's geodesically complete, and, well, it seems to be sort of unique. And in the limit where theta goes to 0, this is just global ADS3, as it should be. It should match the ADS3 case.
Is your f of r the same as that?
Yeah, same f of r.
So it's not unique.
Oh, I'm sorry.
It depends on RH.
Perfect. It's the same f of r, which has an RH. RH to the 2 minus theta. But the point is, I want to keep, to be in the same kind of asymptotic class of geometries, I want to keep the periodicity of this angle 2 pi without having any conical deficit or surplus or anything like that. That's going to fix RH to be a unique number. Thank you. That's crucial. It's something like 2 over 2 minus theta, but it's not important exactly what it is. Good. All right, so with this geometry now, I can calculate, this is some soliton. Well, I'll write it back. The energy of this is this.
So you've chosen a special hole to fit in that space, is that?
Sorry?
So that point you just made with Steve,
Yeah.
you've chosen a special size for the hole?
Yeah, so this doesn't have the interpretation of a black hole anymore, it's just some regular geometry.
Okay.
Yeah, but I've had to fix its size so I can keep the periodicity of this 5 coordinate the same. Otherwise I leave the kind of, right. In holography you want to fix your boundary conditions and work only in that class. And I've fixed phi to be a circle of periodicity 2 pi, and that fixes what RH is. I shouldn't even call it H anymore, it's not a horizon or anything. It's just a number. Okay, so here they are. Here are the two pieces of data that I was looking for. And we won't go through the algebra, but the point is if you plug these into here, you get the correct entropy for the black hole. You get the Bekenstein-Hawking entropy. An important thing to note is it's very similar to the case of ADS3. This is negative, as it should be, and it seems to be, it's at least separated by a gap from the black hole geometries, because the black hole geometries, as they shrink to 0 size, their energy goes to 0, and this is some discrete negative number, so there's a gap between this and the rest of the geometries. If I set theta to 0, that's the ADS case. This goes to 1. That's just the energy of global ADS3. So, it passes the test that it had better pass to have a chance of being correct. And yeah, as I said, you stick it in, you get the correct entropy. So, any questions about that? All right, there's one more thing that, it's sort of trivial, but one should, of course, check. In ADS-CFT, we understand, this is the Hawking page part that I'm moving on to now, we understand that there's some Hawking page phase transition between a sort of thermal gas in the bulk and black hole states. This is a question of what configuration dominates the ensemble. And for this calculation to be meaningful, it had better be that at large temperatures, a black hole is dominating the ensemble. Because otherwise, this would be a formula for the entropy of a thermal gas, and it would be wrong. But again, intuitively, you know that if you go to sufficiently large energies or temperatures, a black hole is just going to win. on entropic grounds. So I'll just kind of write down, I won't go through it, but I'll write down what one needs to do. You need to calculate in any kind of, Hawking page type calculation. You want to calculate the Euclidean action of the black hole, and you want to compare it to, the thermal background. In this case, it's this soliton with thermal periodicity for the time coordinate. And you want to see which Euclidean action is smaller. So that's all it is. It's evaluating that action, the Euclidean version of it. And you want to make sure the black hole wins. In other words, it dominates the ensemble. And the claim, which you can check, is that this is less than 0, meaning the action of the black hole is smaller, if and only if beta is less than 2 pi. So it's the same Hawking page transition temperature as in ADS. There's no theta dependence in it. So that's another check for this application to make sense. All right. So that is the sort of crux of the talk. I gave some motivation at the beginning about caring about the theta goes to one limit and potentially other applications. So let me talk about those for a second. But before I move on, I just want to emphasize that this formalism...
Can I actually ask
Yeah.
you one? Maybe you've said it already, maybe it's just a silly question. But geometrically, why would you think that this should be the good geometry that you would use with the vacuum?
Geometrically, the only
If I'm sort of just naively thinking about the black hole solution here, I mean, I could just naively say, well, the vacuum would be the one for which the mass of the, of the object that sets the geometry up goes to 0, or in other words, the limit RH goes to infinity or something like that.
Good,
but
good.
you're obviously saying that's not happening here.
Good.
And if you actually take that as a reference frame relative to which you define vacuum energy, you're getting the right. So what is it in the geometry that tells you this?
Good. So I can. There's no proof. Okay. So, but I can rule out. Yeah, exactly. One might think that if I just take the black hole size to 0, that should be the ground state. But I can rule that out in the following way. If I take it to 0, I can compute its energy, and it's 0. If I compute the energy of this thing, it's negative. So this thing definitely has less energy than the 0-sized black hole. But I haven't proven that it has the least energy, or really that it's unique.
This sort of reminds me of these. There are these strange vacua for the BTZ black hole as well, right? Where
No.
something.
Well, for BTZ, it's just pure ADS.
Yeah.
But for ADS in general, black holes in higher dimensions, there's this ADS soliton, which looks a lot like that.
Yeah.
There was some. I don't remember anymore. There was some business with these. Never mind. I'll try to remember later on.
Yeah.
That's okay.
Yeah, but it is
Some,
true that
the
this.
Kalb-Ramon versus Nevers-Schwartz vacua.
Yeah, but that's ADS versus M=0 black hole.
Yeah.
Yes, that's right.
Yeah, so this is
That's right.
more like ADS.
Yeah, exactly. But yeah, this one I set theta to 0 is exactly global ADS3, and that's the sort of correct vacuum to pick to reproduce the BTZ black hole entropy. Okay. So right, you can try and prove this, and I'm trying to prove it right now with some sort of kind of positive energy theorem in the bulk. You show that it's not positive because it's negative, as I said, but the energy is minimized at this configuration. That's something you can hope to do.
For my own education, there was one other thing that has been confusing me throughout the talk.
Good.
Which is, as I was trying to remember these solutions and so on and so forth, and I think what makes them particularly tricky here to connect to some of the things I do remember is the specific parameterization of the coefficient of that exponential in terms of the thetas, namely the same parameter that appears in the exponent as well.
Yeah.
Right, in many of these stringy actions, actually, you have the exponent, and let's say you call the parameter, the numerical coefficient there, theta, you often do not get the coefficient as well, or the overall, number that multiplies the exponent to depend on that same theta as well. What I mean is that I can imagine many actions where in the exponential I can take the limit theta goes to 1 or whatever, something happens, but that does not simultaneously kill that term altogether.
Oh.
Right. So what I'm really asking is, so what specifically motivates this normalization
So theta goes to 1, I know you meant it generally, but theta goes to 1 should kill this term because in the case where it's flat space, you know you just want Einstein gravity as the solution. So,
I know, but that's a bit of a reverse engineering of sorts. What I mean is, suppose you take some string theory action in, let's say, 10 dimensions, and you
Yeah.
dimensionally reduce it.
Yeah, you get something like this.
Not necessarily, you get something like this, but not necessarily with that same coefficient multiplying the exponent.
I claim that you can parameterize it such that you get exactly this. I think that's a true
In all
statement.
cases.
No, in all cases. Well, in 3 dimensions. I mean, the point is, okay, so this maps onto the case of a stack of D1 branes, for example. That's the case where you have some 3-dimensional non-compact geometry and some sphere that goes along for the ride. And my claim is that if you dimensionally reduce along the sphere, you get, for example, exactly this geometry with theta equals -1, I think it is. And there, the action can be written in this way.
So
But, yeah.
that may be, right. So I guess we'll just have to sit down and compare the notes.
Yeah. I mean, the relationship between the factor in the exponent and the factor
Yes,
in
yes.
front of
Very
the
good. Right.
exponent is arbitrary, though, because you can always just shift phi by a constant.
Oh, I
And
understand
that
what you're asking.
changes the,
Multiplicatively, yes, but
Multiplicatively.
nevertheless, both have, both do funny things in the special limit theta going to 1, which is, I think I can also come up with examples where such special limits do not occur. And so I'm not doubting that this happens. I'm merely trying to figure out what is the special situation from which this arises. But maybe we should talk about those details later.
Sorry. Yeah. There are freedoms you have. For example, even in between the on-shell value of phi and this exponent here, you can
Right.
shuffle stuff back
No,
and
no,
forth.
certainly there is that multiplicative freedom. That absolutely is true. That gets absorbed by shifts of phi. But nevertheless, there is this degenerate limit of sorts where, theta going to 1.
Yeah. So
Anyway.
okay. So let me talk about two quick sort of an extension of this. So one thing that was first sorted out by a member of the audience is that once you have the Cardy formula and you apply it to the BTZ black hole, you can do something else which is kind of cool, and you can get sort of logarithmic corrections to the black hole entropy formula. So this is, of course, due to Carlip. So so if you want to do that, for example, you can sort of, start using the little bit fancier notation, if you want, that's kind of familiar from 2D CFTs, and you can sort of write, let's say, the partition function in this way. So I'm not going to really go through I'm just going to outline it and tell you what the answer is. And so in this parameterization, Q is e to the 2 pi I tau, and tau is the modular parameter of the torus. I'm going to restrict, like I have throughout this talk, to tau is just I tau 2, meaning I have no angular potential, meaning these black holes are not spinning. So I'm just going to restrict to a square torus. It's just a finite temperature, no angular momentum. And then, the sort of So that means that I don't really need this, tau bar language. That's a bit too fancy. So this begins to look something like this. I can sort of pick out the degeneracy by some sort of integral like this, and now all at once I could see that I could evaluate this integral by a saddle point approximation. And again, as Carlos pointed out, in the saddle point approximation, you can go to subleading corrections and pick up the subleading corrections in the saddle. And if you do that, then you generalize his result. So if I write it in bulk language, here's the Bekenstein-Hawking entropy. And you can write the entropy. So once you do the saddle point approximation to quadratic order, you can write the entropy like this. So this has the usual form that we've seen in sort of the BTZ case, that there's a famous factor of 3/2 in front of it. And these thetas kind of change that scaling. Now you get something that looks like this. So you can get the sort of leading logarithmic correction as well, just by this formalism. Okay, very good. So that's just a quick additional point about this, and this is something that you can now go and kind of try to check with some sort of analogous bulk calculation. But all right, since I'm almost out of time, let me finish with saying what happens and the theta goes to 1 limit. So I guess I don't really need this anymore. So since all this stuff kind of breaks down when you set theta equals 1, I can erase it, although I'll keep the black hole solution. So when I set theta to 1, this thing that I call a black hole geometry is just Rindler spacetime. Okay? It's 2D Rindler across a circle. This factor cancels. There's just a d phi squared sitting by itself. So it's just 2D Rindler across a circle. And this is, of course, an important geometry to understand because Rindler is sort of the near horizon of generic non-extremal black holes. If you zoom in close enough, you get a Rindler spacetime. Of course, you usually don't have the usual notions of decoupling and things like that, but nevertheless, you get Rindler. So you can ask what happens as I take theta goes to 1 in my formulas for the black hole entropy. And this is just numerology at this point. So what you find is that the entropy looks like this. So in the usual case, I had that the entropy was kind of some combination of the energy of the black hole case I'm interested in, and then the vacuum energy. In the limit of theta goes to 1, it's sort of completely dominated by the vacuum energy. This piece falls away. And you get something like this, which is also something familiar when people write the entropy of Rindler in terms of the dimensionless Rindler energy. And evac is equal to minus L over 4G. What's evac in this case? Well, if in the limit theta goes to 1, this is Rindler, then I swap this piece over here, then the vacuum configuration is just flat space. All right, so now you should say, well, if it's just flat space, why did you assign it a negative energy? So this is the weirdness of this limit. All the calculations were done at r equals 0 in the spacetime, because that's where the conformal boundary is. Of course, when you send theta to 1, that's no longer the conformal boundary of the spacetime. That's just some weird intermediate point in the geometry. So even though all this stuff is kind of breaking down, the entropy seems to come out correctly. It's just the kind of area of this circle, which is 2 pi divided by 4g. And these L's aren't really here, so I can scale away these L's. So it's really just 2 pi over 4g, which is pi over 2g. And again, I emphasize that this is basically numerology. I think it's continuously connected to a bunch of examples that work. Therefore, it's probably guaranteed to work because it's connected in that way. But it would be interesting if there's some other way to understand why this theta goes to 1 limit is actually giving you something sensible. The other thing that I didn't have time to get to is people consider, I'll just say a few words about it, people kind of consider anisotropic generalizations of this background. They're called Lifshitz spacetimes. That's where time scales differently from space. And you could extend this formalism to those cases and reproduce the entropy of those black holes, and you also get you can get the logarithmic correction, and in that case it looks like this. So you can get the logarithmic correction where you have a dynamical critical exponent z, and what's called this hyperscaling violation parameter theta, and that seems to be the leading logarithmic correction. But anyway, that's it. That's all I wanted to say. Thanks.
Question and a comment. The question is, can you do this for the rotating case?
So the formalism that I set up of rescaling the L's and stuff, so I wrote that down in the rotating case to get a formula out. I mean, I didn't really publish it because I didn't have, there don't exist black holes as far as I know that are asymptotically of this form and are rotating. So I didn't have a black hole to check it against, so I didn't really bother writing down the formula. But I think it should carry through, and I listed it as an important check of this kind of formalism to test something like that. Yeah.
And for your flat space vacuum energy, I don't know the answer to that, but in the two-dimensional CFT, you're looking at the energy on a cylinder rather than a plane. It's the Casimir energy. So the question is how you map Rindler to a cylinder, or the asymptotics of Rindler to a cylinder, I think. And I don't know how to do that. This is somehow it's somehow the vacuum energy that you would get with no, it's peculiar. It's twice the central charge, right?
Right.
So, yeah, I don't know where that factor of 2 comes from.
Yeah. I mean, as far as I understood, it was just kind of some weirdness of evaluating stuff at r equals 0, which, if you write it as Rindler, it's just some kind of, it's like, it's some like coordinate here or something. There's like r equals 0 or something, there's r equals infinities out here, and it's sort of evaluating it. There's a different r. It's sort of evaluating on some slice here, but it's a weirdness of taking the limit. But maybe that, as you say, maybe there's a way to understand, right, mapping that to a cylinder and seeing that indeed it should come out negative, but
Yeah.
I'm not sure I understand it.
There's a paper from about a year ago in Loop Quantum Gravity by Eugenio Bianchi about Rindler energy, and I don't remember if this is what he gets, but he has an argument for what the right boundary term you need for Brown-York energy is in Rindler space. It might be that.
Yeah, I'll take a look.
That's worth looking at.
I'll take a look, thanks.
There is no more questions. We can thank everyone once again.